Welcome to the next video in the mathematical logic series on propositional logic. And in this video, we'll be discussing Boolean functions. The fundamental object that we'll study in propositional logic are sentences that must be either true or false and cannot be both. So there are some sentences which are neither true nor false, like here I have on the slide an exclamation like hey. There are commands like go west, and those are neither true nor false. Here in propositional logic, we focus on those sentences which must be either true or false and cannot be both. And often these things are called propositions. We will be talking about the truth or falsity of these propositions. That is going to be the basic semantic object, right? True and false are going to be the basic semantic objects of propositional logic. So right now we're talking about semantics. Often use the number 1 as kind of our symbol for true, and the number 0 is our symbol for false. There's no deep reason for that. We just need, it's just an encoding. It's not like meant to communicate anything. So just when we write 1, what we mean is true, basically. And so on. So the next thing that we want to define, still in the realm of semantics, this whole video will be focused on the semantic side, is the idea of a Boolean function. And to get started, let's talk about the conjunction function. It is meant to we will eventually talk about conjunction sentences, and we will evaluate their truth value using these Boolean functions. But just to get started with, let's understand that we write these Boolean functions in a matrix form like this. And that's meant to be read as a sort of table for values of A and values of B. So along the rows, you could imagine the possible values that A might take, and along the columns, you could imagine the values that B might take, and then the values that you see inside the matrix are is just some mapping of inputs to outputs, right? So if A and B, or really the inputs are 1 and 1, then the output is 1. So that's the first part of conjunction. It's kind of like saying if you have true and true, it evaluates to true. Whereas if you have, say here, that would be true and false evaluates to false, and all the rest of the familiar story with evaluating conjunction. And so that is the truth value matrix for conjunction. To generalize this idea a bit, we can talk about all binary Boolean functions, and that would basically be the same as all 2x2 matrices with coordinates 0 and 1. So your input could be any pair taken from 0 and 1, and you will output a 0 or a 1. And so the set of all such things is a binary Boolean function. So from basic counting principles, we know that the domain so the set 0, 1 has cardinality 2. Since we are squaring that set, right, we're taking the Cartesian product of it with itself. Then there are 2 to the 2 elements within the domain. And then since the range has size 2, then by more elementary counting principles, 2 to that power must be the number of all such functions, just as a demonstration of some of what we're talking about here. So one of these functions would be the disjunction function, and I'm not necessarily going to talk about it because it's pretty obvious, right? It's just going to have a matrix that looks like that, right? So should be familiar from a previous symbolic logic course. So to backtrack just a little bit, we can also talk about unary Boolean functions, which will input just a single 0 or a 1 and output a 0 or a 1. By similar counting principles, we know that there must be 4 of these functions, but we'll only ever really care about one of them, which is the negation. so that if you plug in 0, you get out 1, and if you plug in 1, you get out 0. Okay, so generalizing from unary and binary, we can talk about n-ary Boolean functions, which have as their domain the set 0, 1 to the n, right? So n Cartesian products of this set with itself, and always with range 0, 1. So any function like that is called an n-ary Boolean function. And by similar counting principles to all of what we saw before, there are 2 to the 2 to the n such functions. And in particular, we can even talk about certain constant functions, namely, right, it has no inputs and just always takes the value 0. Well, that might as well basically just be the same thing as the number 0. So it is, sort of this constant function 0, and likewise with 1. Just as we don't really give names to 3 of the 4 unary functions, we also won't give names to the vast majority of binary functions either, and we won't give names, I think, to any of the other n-ary functions. And the reason for that is we can actually use the components of negation, disjunction, and conjunction. Really, we only even need negation and disjunction, but in any case, we will see a proof later on that, in fact, we don't need to give names to all those other functions because we can actually express them through constructions using this much smaller set of named functions.